Hi, today we're looking at the PAT paper from 2010, going through questions 17 to 21, the second lot of multiple choice questions. So in question 17, we're told that a ray of light which travels perpendicular to the line of intersection of two mirrors M1 and M2 reflects off of M1 and then off of M2. And we're asked what angle is the beam turned through relative to the incident beam. Well, let's draw this on. So we have, first of all, our normals to the mirrors. Let's have our ray striking. So it's perpendicular to the line of intersection. So that's a line here coming out of the plane. So it's going to be travelling like this. It'll strike us on angle theta, and so this is 90 minus theta. We know that angle of incidence is the same as the angle of refraction. So if we say it then reflects off, it will also reflect off at theta. As that's 90 degrees, it follows this is also 90 minus theta. And again, as the angle of incidence is the same as the angle of reflection, that is 90 minus theta. And we notice immediately that this line is parallel to this line. And they're both rays of light meet the parallel lines at the same angle. And so we see they must have turned through exactly 180 degrees as it's travelling in the opposite direction. So the answer is turn through exactly 180 degrees. So in question 18, we're told a capacitor of capacitance 3 nanofarads is charged with a voltage of 10 volts. And we're asked what is the charge held by the capacitor. Well, we know that Q is CV, where Q is the charge of the capacitor, C is its capacitance, and V is the charging voltage. So simply subbing in, we get Q is equal to C, 3 nanofarads, so 3 times 10 to the minus 9, times the voltage 10 volts, which is equal to 3 times 10 to the minus 8 coulombs. So in question 19, we're told that a car suspension is sat on by a person of mass 80 kilograms. We're told that it has a spring constant K of 80,000 newtons per meter, and we're asked how much is it compressed. So let's visualize this. So we have our spring here, and we have some mass of 80 kilograms. And we know that when it's placed onto the spring will produce enough force to balance the weight of the object. So basically there'll be an equilibrium in the system when the system comes to rest. So we have a force downwards of 80 G, which means that the force upwards from the spring must also be 80 G. We know from Hooke's law that F is equal to K delta X, where delta X is the extension in the spring. So therefore we have that K delta X must be equal to 80 G. Subbing in, we get 80,000 delta X is equal to 80 times 10, which tells us that delta X, the extension, is equal to 800 over 80,000, and therefore delta X is equal to 10 millimeters, the extension in the spring. So in question 20, we're told that a comet orbits a star, and we're told that at its closest approach, it is at 4 times 10 to the 10 kilometers with a speed 50 kilometers per second. And how fast is it travelling at the maximum distance it is away from the star at 10 to the 10 kilometers? Okay, well, Kepler's second law tells us that, well, if we have the star here, and we have its closest approach, which is a distance a, at which it travels with speed u, well, Kepler's law tells us, sorry, that should be from the origin of the star, the centre of the star, A, Kepler's law tells us that if it's travelling at v at the furthest distance away, which is b, UA equals to BV. This is a result he obtained from observation and measurement. So what this tells us at subbing in, well, we know U is 50 kilometers per second, and we know that A is 4 times 10 to the 10, so 4. We know that V is, well, V, and B is 10 times 10 to the 10, so that's just 10. And this tells us that V is equal to 50 times 4 over 10, which is equal to 20 kilometers per second. So in question 21, we're told that a fish is seen to be at an apparent depth of 0.75 meters. And we're told that the refractive index of water is 1.33. And we're asked what is the true depth of the fish. Okay, so let's draw this. So here's our water interface, and here's our normal. So let's just draw our fish here. So you can do a better one than that. So, okay. So we have some ray of light coming here, and then it refracting and going towards the fish. So this distance here is the true depth of the apparent depth, 0.75 meters. In the same way we can define the refractive index with the ratio of the speed of light in the fluid to that in the vacuum, we can do the same with the distance. So we can say the refractive index is equal to, well, the true depth, d real, over the apparent depth, dA, which is equal to d sub r over 0.75. So 1.33, which is 4/3, is equal to d sub r over 3/4, which tells us the true distance is 1 meter.